Okay, so now we're going to turn to something a little more practical. Okay, so we've talked sort of at a high level what DFT is and what the various terms in the Hamiltonian represent, why we calculate them, but we don't know how we calculate them. Okay, and in order to calculate any term in the Hamiltonian, in order to get any result, we need to choose a basis. Okay, we talked about bases yesterday briefly, but effectively, a basis is a framework, is a representation for the mathematical objects that we are dealing with. So, non-interacting 3D wave functions are the main one. Okay, we might also use a basis to represent the density and the potential, not necessarily. Right. So the two bases that we talked about yesterday are plane wave basis and a linear combination of atomic orbitals. Okay. Linear combination of atomic orbitals, in that kind of grouping, I also include Gaussian basis sets, Slater basis sets, and numerical atomic orbitals, or NAOs. Okay, they're all kind of in that non-orthogonal, atom-centered linear combination of orbitals. Okay. What we're concerned with is none of those, but with plane wave basis sets. Okay. The reason being that we're talking about materials calculations, we're talking about solid state calculations in general. Okay? So the basis set that we are concerned with is plane waves, and the basis set is is easy, right? Is like everything that we deal with, it's easy. Okay? It's just, it only becomes complex once we introduce all of the various parts of the Hamiltonian, all of the various parts of the calculation, and put it all together. And it looks complex as a whole, but if you zoom in on any one part, it's always easy. The chemistry kind of side of things is more complicated if you zoom in on one piece, but it has its own simplicity in a way. Okay. For instance, in chemistry, they are not worried about summing over the Brillouin zone and dealing with K-points, simply because their systems are isolated. If our systems are periodic and extended through space, we need to sum over the Brillouin zone, right? All right, anyway, let's begin. So this is a normalization factor, 1 over the square root of the volume of the system. We'll just ignore it for now, and just we'll say that our plane waves look like this. We'll say that if we're starting at an origin in reciprocal space, or even in real space, we're starting at a point and we're going along a vector, right? That vector is the direction that our plane wave is going in. And so if we're going in that direction, what we're effectively looking at, I need a prop. What can I use? This? No, this. Yeah, okay. So what I'm looking at is actually a pressure wave in that direction, okay? So if I was to stand in front of you with this thing and push air towards you, right, the air will be compressed in front of this thing, and then the air will be less compressed here, so the air will want to flow into the low density region, and then the air in this region will want to expand again and contract, and we'll have a pressure wave heading towards you with planes of high density, low density, high density, low density, high density, right? So when we're talking about a plane wave, we're talking about a pressure wave, okay? But we're talking about a standing pressure wave. So it's more like if I had two nodes, and I ask the question, if I resonate the air between the two nodes, what standing waves can I get? I.e., they're not moving in time. Okay, right? So we have this standing wave, which is going in that direction, high, low, okay, in that direction. If k, right, is our wave vector, k has a magnitude and a direction, okay? So the direction is obvious, it's just the direction that the plane wave is going in. The magnitude is the frequency, okay? So if I increase the frequency of k, of course, the distance between our wave fronts decreases, and we have a faster plane wave, okay? Faster, higher frequency. Okay, so that's what we're talking about when we're dealing with plane waves. In order to use that as a basis, what we have to do is this, okay? So we're effectively setting our wave functions, I'll call that I, equal to this, right? But in order to use it as a basis, what we actually want to do is we want to do a sum over a bunch of coefficients, okay? So I'm going to say something like that, okay? So I'm going to have a bunch of coefficients which are summing over plane waves of various frequencies and directions, okay? And what we're effectively doing here is a Fourier transform in reverse, okay? So if you think of this chalk keeps breaking, okay? If you think of a wave, right, and we want to approximate that in a Fourier series, and you think of a sine wave as the first mode, and I want to add more terms in order to approximate the square wave. What we need is, for a square wave, we need a third of the third harmonic, right? So I don't know whether that's a third, but we're going to end up with something that looks more like this. So something that looks a bit like that, right? And then we can add the fifth harmonic, a fifth of the amplitude of the fifth harmonic, etc. Okay, and it's the same idea in 3D with our wave function. We are adding higher and higher frequencies in order to create the Fourier transform of our wave function. Okay, that's all we're doing. Right, enough of the background. Enough of the background. Okay, so we need to be able to. Okay, one more thing on background. Okay, one more thing on background, which is the advantage of using plane waves is they're orthogonal, so we don't have to deal with the tensorial nature of our wave functions. Okay, we don't have to deal with covariant and contravariant. Okay, we can just assume everything's the same. And importantly, we have systematic improvability. As we make k bigger, okay, as we add more plane waves, we improve the Fourier transform of our wave functions. And so, if we add more plane waves, we get a better result. Okay, systematic improvability. This is very different to a Gaussian basis set. Most Gaussian basis sets, in that in a Gaussian basis set, you may add, another zeta. Okay, you may add another polarization function to your Gaussian basis set, and your result may get worse. That does happen, right? With a plane wave basis set, you add more basis functions, your result will get better. Okay, systematic improvability. All right, come on. Right. So what we want to be able to do is to represent all of those terms in the DFT functional in terms of our basis set, in terms of plane waves. So if we take a look at our kinetic energy, the operator, right, and we apply the kinetic energy operator to our plane wave basis set, effectively all we're doing is we're taking our plane waves and taking the second derivative of that. And so, of course, this is very easy. We just drop down. We're taking the derivative with respect to space, right? So we just drop down. We drop down this, right? And then take the second derivative, get a -1, k squared, right? And we've already got the second derivative of our basis set, and we've already got the kinetic energy, right? Just dot product that with the other side, and we get our kinetic energy result. See what I mean, right? It's simple. Okay. One more thing. So remember, we wrote down the Hamiltonian matrix, Ij, right, is like this, and we've got H11, H12, etc. Okay. If you say one of those terms is going to be e to the I k I dot r, right? Because our so I've put an index on the k's, right? So I'm saying ki and kj, right? Because our plane waves are orthogonal, if I and j are not equal, this whole thing is 0. Okay, which means that our Hamiltonian matrix in a plane wave basis is diagonal, and we do not have to worry about off-diagonal terms. Okay, so everything becomes easier when you use a plane wave basis set, and faster, right? All right. Right. So we get the idea on how to calculate the kinetic energy. What about terms that involve the density? Right. What about terms that involve the density? So, for instance, here we have the Hartree energy, or the electrostatic Coulomb interaction between the electrons. And so we have the Hartree potential, and we have an integral of the product in space, the pointwise product of the Hartree potential with the density, right? So if we look at the Poisson's equation, which is one way to calculate this, what we effectively have is this differential equation. All right. So I prefer, actually, never mind. Just do it the same way that it's on the screen. So what I'm going to do, I'll probably write that as an N or whatever. All right. What we're going to do is we're going to look at both sides and expand them both in terms of a plane wave basis set. All right. So if you just write that in, and so we're summing this part, we've got some coefficients, and we've got some plane waves. Did we use G or we use G? Okay. Write it the same. Okay. So we've got some other coefficients here. Using VH or whatever. Right. So on both sides, effectively, we're going to have a very similar situation, right? We're going to have a very similar situation. We've got the second derivative operator, and so everything apart from the plane wave is going to be constant with respect to the expression, and so we're just going to get a second derivative over here, right? So it's the same deal again. We're just going to have a minus. We're just going to have a g squared, and then we're going to have the sum over our what do you call them? Coefficients. Okay. And on the other side, we're going to have a minus 4 pi. We're going to have a bunch of coefficients, and we're going to have our plane waves. Okay. So if we look on the next slide, you can see that on this side we've got a g squared, and we've got a density on the other side. We've got a why have I done it the wrong way around? well, whatever. It's just everything becomes 10 times more difficult when you're doing it on a board. You just can't quite see everything. Never mind. Okay. So let's put a v in here. Let's put a density in here. Okay. And so if we just divide through, and write in terms of like this. I don't need to write it down when I've got it on the slide, right? Okay, so if we just write it down like this, and we see that we've got the Hartree in terms of the in terms of reciprocal space, in terms of wave vectors, right? What we can do is just dump that into the expression, and we can calculate the Hartree term. Okay, so maybe I can explain that a little better. I need to take it. The problem is I have two competing demands, right? I need to go fast because I know that we're late. We need to be going faster. But on the other hand, I need to go slower so that I don't confuse myself as I'm doing it on the board, right? So two competing demands, right? So what we want to do is we want to calculate the Hartree term in reciprocal space, in a plane wave basis. Okay, so the first thing we need to be able to do is write our density in terms of plane waves. Okay, so all we're going to do is remember that our density is written in terms of our states, right? And then all we're going to do is replace our states with our plane waves, right? We've got to remember that plane waves are orthogonal, so we only care about these ones. All right, ik dot r e to the I k dot r, summing over all of them. So we put that into the Hartree expression, Hartree potential. We have an integral over the density d of r. All right. So if we replace our density with that thing, right? We can write our density in terms of plane waves, right? That implies to us that we can take the Fourier transform of our density, right? So if we say that our density Fourier transformed right? If we take the Fourier transform of our density, right, then what we need to be able to do is to write our potential also in reciprocal space. We need the Fourier transform of our potential. Right. So effectively, what we need to say is what is the Fourier transform of our potential, and how do we write it in terms of the Fourier transform of our density, right? And what we do is this: we just multiply by our operator in reciprocal space, which we worked out earlier, right? So this thing, right? If you see that you divide through by 4 pi, right, and you get a density, right, you can see this expression here, right? If I say that you see what I mean, right? This, well, okay, it's written down here. So we just replace our Hartree potential in reciprocal space with this expression in terms of the density, and then our operator is just 4 pi over g squared. Right. So once we Fourier transform this expression, that's step one. The next step is to take 4 pi over g squared. So g squared is just our is just the squared magnitude of the plane wave, okay, in the basis, density in reciprocal space squared, right? If we take that expression, okay, we take that expression and sum over G. I keep writing K. I don't know why. Never mind. Right, G. Right. So if we sum over G there, then what we get is V of K, right? And then if we want V of K in real space, all we have to do is take the inverse Fourier transform of V of G e to the I G dot R dg, right? And that gives us V of R, right? So it's a simple thing. Fourier transform the density, multiply by the operator. If you want to get the energy, sum over G. If you want to get the potential, don't sum over G. Do that, right? Now I've got the Hartree potential in reciprocal space. I want the Hartree potential in real space, inverse Fourier transform, right? And so why is this better? Why is this better? Because this operation is an n cubed operation, right? Each Fourier transform in each direction, in each dimension, x, y, z, right, is an n log n operation. Right? So if I do a Fourier transform in one dimension, it has scaling n log n. If I do a 3D Fourier transform, those three dimensions are orthogonal, and the three Fourier transforms are orthogonal to each other. So this scales cubed, right? And so I have one cubed operation. Then I have an operation over every grid point, which is n cubed operation. Okay, so basically I have to look at every single point in my space, right? But all I'm doing is on every point I'm multiplying the square of the frequency by the square of the density at that point. It's just a n cubed operation, right? And then I do the inverse Fourier transform, which is basically n cubed. So the whole thing, this is trivial. So the whole thing is basically 3n cubed operations. 3n cubed operations, right? So the Hartree expression has written, I don't think I've actually written it down, but the Hartree expression, this, okay, this is an n cubed operation, right? But if I want the energy, and I do it naively, right, I need this thing, right? So if I get the energy naively, I need to take the derivative. So I need to take the integral of the density in this way for every single grid point, right? And what you can see is that I have an R primed here, right? So for every point R primed, I need to do this n cubed integral, right? So to get every point R primed, I need to do one n cubed integral. So in total, to get E, I need to go over every single R, let's put this as R primed, right? I need to go over every R primed point. So the whole thing is n to the 6 scaling, right? Do you get that? I don't think I explained it very well, but the point is, this integral is over R, okay? And the output argument is R primed. So for every R primed in space, I need to do this whole integral over all of space, okay? So if I have a point, I need to do the whole integral over all space. And then next point, whole integral over all space. Whole integral over all space. And once I've done it over all space, I get that thing, right? And that thing I need to integrate over all space. Okay? So that is n to the 6 scaling, right? But if you write it in reciprocal space and do it this way, you get 3 n cubed scaling, which is much, much, much faster. Okay? So it's using a plane wave basis set is beneficial in this way. However, you always get something bad as well as something good. The problem is when you start to maybe just push this over. Right. When you start to worry about the electronic nuclear term, right? The external potential, we have to remember that the external potential looks something like this, and on our nuclei we have a singularity. Okay. Now, Fourier transforming a 1 over R potential is not computationally efficient. Okay. Problem is that if we want to Fourier transform this, to get any kind of accuracy, we need something like infinite terms, right? Okay. So right. So if we Fourier transform the nuclear potential, the 1 over R, right, we just can't do it. We can't Fourier transform that without needing an extremely high number of terms in order to accurately capture 1 over R in reciprocal space. Okay? All right? So what we do instead is we cheat, and we do I have? No, I don't. Okay. What we do is we cheat, and we say, well, we can't do 1 over R, but what we could do is we could approximate this this nuclear potential close to the nucleus in a way that doesn't require very many terms to Fourier transform. Okay, so if we're saying that this is our V external, something like that, right, and we want to take V external, we want to take the Fourier transform of that thing, what we need is something which doesn't require too many terms in order to Fourier transform it accurately, right? And so effectively, the Fourier transform is just doing something like that, right? Avoiding the singularity, drawing in something which is bandwidth limited, right? So the whole problem with the Fourier transform is bandwidth, the number of frequencies we need in order to represent the function. So if we can instead replace the 1 over R with a bandwidth limited alternative, which is in some way correct, then we can do the calculation accurately, right? But the question is, what is correct? And so what we effectively do is we say, well, what we do is we say, within this sphere, right? So this is an atom with a sphere around it, and that's RC, right? So RC, we say within that sphere, we don't have any chemistry going on, right? We say within this sphere, this is core electrons, and within the sphere of core electrons, all we have is core electrons, okay? We say outside of this sphere, we have the valence region, we have valence electrons, electrons which are interacting with other electrons. So in the core region, we say the electrons are only interacting with electrons from this atom, okay? And so effectively what we say is we just need to find the radius of the core region, okay? And if we can find the radius of the core region, we can make we can make the potential within that sphere effectively anything you want and not affect the valence chemistry of the overall system. Right? So this is the idea of a pseudo potential. Okay. Now, how long have we got left? How long do we have left before the bell comes on again? 10 minutes, okay. Right, so let's move on. So electron density, okay, right. So things like exchange correlation energy, at least in a semi-local approximation, are the same, right? Because all we have to do is Fourier transform the density, and it's a very similar expression. Okay, so we don't need to really go into the exchange correlation in too much detail. In a plane wave basis set, it's very similar to calculating things like the Hartree potential. All right. So, okay, it's cut off. Never mind. All right. So let's go into this. Why is it not loading? Is it working now? Okay, fine. Right, this didn't quite fit on the slide, so let's pull it up here. So the final piece of the puzzle, in order to put together a full DFT calculation, is to converge it, right? Because what we have to remember is that these equations that we are solving are nonlinear, okay? So it's not like we just get the right form of the Hamiltonian, solve the equation in one pass, and get the energy. Instead, we have to self-consistently minimize the energy in order to variationally head towards the lowest energy of the ground state. Okay? So it's a loop that we go around multiple times, right? So you start with an initial guess for either the density or the potential, right? Depending on what kind of calculation you're doing. But let's say we start with a density, and you can start with anything you like, right? So if we say, I have a system, it's 10 by 10 by 10 angstroms cubed, it's a cubic cell, and in that space I've got, I don't know, 4 atoms, it's an FCC crystal, and those 4 atoms each has 3 valence electrons, okay? What I can do is I can say, well, I'm gonna have 3 by 4 total electrons in my system, okay? So I've got 12 electrons to deal with, and those 12 electrons, I can say I'm going to have a density which is just, on average, 12 electrons everywhere. Or I can just put random numbers into my density and say my 12 electron density is just normalized to 12. It's a box with 12 electrons in it, okay? It's a guess. We don't care what it is. It can be anything, right? So long as it has the right number of electrons, okay? All I need to do with that density, is to calculate the effective potential, the Condensed potential. All right. So the potential, the Condensed potential is the Condensed Hamiltonian. So effectively, all we've got to do is take all of the density-dependent terms, Hartree energy. So this is electrostatic electron-electron interaction, external potential. This is electron-nucleus interaction, and exchange correlation energy, potential. Those 3 terms, feed the density into them. So, you know, we've got it written here. We take our guess density, Fourier transform it, calculate the Hartree potential, and inverse Fourier transform to get our Hartree potential in real space. Okay? So that's our Hartree potential. We calculate our external potential using pseudo potentials, and we calculate our exchange correlation functional using whichever exchange correlation functional we choose to use, LDA, GGA, whatever, right? We get V effective, and then we get this matrix, right? We get the Hamiltonian matrix that we wrote up earlier. Okay, so it's H, I, J, and we just need to diagonalize that Hamiltonian matrix. Okay, we diagonalize it to get the eigenvalues and the state vectors. Okay, so these are the coefficients which are multiplying our basis vectors. These are so we've got a certain number of basis vectors of plane waves, and for each plane wave we have a coefficient which multiplies that plane wave, and when you sum all of the coefficients times the plane waves, we get our Fourier transform of the wave function. Okay? So effectively, what we get out of this is some eigenvalues and eigenvectors which represent our wave functions. Okay? If we have new eigenvalues of the energy, we can calculate new occupancy eigenvalues. Okay? Let's talk about that. There's never any space. Right. So we know from physics of fermions. So what we're dealing with here is, I can't write and speak at the same time. Right. So what we're dealing with here is a Fermi-Dirac distribution, because we've got fermions. They're distributed as fermionic particles, right? They have a Fermi-Dirac distribution. Okay. So what we can say is that F of, okay, looks like that. And so we can say that we have a distribution which looks, I don't know, something like that. Okay. This is going to be mu, and this is 1 over the temperature. Okay. In atomic units, it's just 1 over the temperature. Right. So for low energy states, they're going to be occupied. We're going to be getting 1, and for high energy states, we're going to be getting 0 occupancy. Right. So it's very easy to calculate new occupancies once we have our energy eigenvalues. We just take our energy eigenvalues, feed them into the Fermi-Dirac distribution, and get the occupancy of our new states, which we multiply by the square of the wave functions for real states to get our new density. Okay, so this was a guess density. This is our improved density. Okay, so we took a density, put it through the Cohen-Sham equations, get a new density, and then we do some magic to the density, right? So just ignore this step for a minute. But what we do is we check, is our density the same as the old density? Okay? Or has it changed? Well, it's the first step, so it's changed. So now we need to go back, and we feed our density back in again, and we go through, and we keep going around until something has not changed. Okay? It may be our density, it may be our energy, whatever we choose to use as a convergence test. Right? That's basically DFT with a plane wave basis set. That's everything. Okay? Apart from the very last thing, the very last two things, which are mixing. If we're doing a mixing scheme like this, right? What we're doing here is we're saying that rather than just taking the whole new density, we're going to mix it with the old density. Okay, so this is the old density, this is the new density, and instead of just taking the new density and feeding it in, taking the new density, feeding it in, what we're doing is we're taking a linear combination of the old density with the new density, right? And the reason for that is to avoid something called charge sloshing, right? So this is a pathological issue in SCF calculations like DFT, which means that if we have, for instance, two atoms, right, and we have a lot of density over this one and not very much density over that atom, what tends to happen is charge sloshing. So this process of going from here to here is likely to move most of the density from areas of high density to areas of low density. Okay, and of course, what happens here is exactly the opposite. So what we will get is a resonance, right? And this will cycle back and forth from here to here to here to here to here to here, and we will not get convergence in our calculation. Okay? So often when you run a DFT calculation and the energy doesn't go down, you expect that the energy will go down that way, right? But often when you run a DFT calculation, it doesn't converge, and you're getting something like that, and it hasn't gone down, right? What's happening is you're getting charge sloshing from here to here to here to here to here to here, right? And so because you're getting this kind of resonance, what you need is a damping, okay? You need to damp this resonance. You need to make it not resonant anymore, okay? And this is the point of having something like a mixing scheme, right, where you only add in some of the new density. So if I take a linear combination of these two things, well, right in the middle, the linear combination looks something like that, right? And so that's completely taken away this resonance, right? So this is called linear mixing. This is the very simplest mixing scheme. There's many, many, many complicated mixing schemes which exist. No, because oh no, no, because if you imagine that you've got the correct density, perfectly correct density, and you feed it into here, the new density will be exactly the same as the old density, right? And so if I put the correct density into here, I'm actually just mixing the correct density with the correct density, because the new density is the same. And so once you reach convergence, you're actually just mixing the correct density with the correct density. And so you never actually change the final result. Now, okay, there's maybe a caveat to that, which is because you're dealing with a variable space which has many dimensions, you have potentially changed the direction that your optimization goes in that state space, right? So with the caveat that you may get a different result because your optimization has gone in a different direction in optimization space, right? But that doesn't mean that it's wrong. It just means that you've gone in a different direction potentially. Okay. Right. So mixing schemes, right? So linear mixing is what we just said, but more commonly we use something like Poulet mixing. Peter Poulet. It's named after Peter Poulet, or it's named DIIS. So he named it DIIS. DIIS. Or Broyden. Right. Just know that those exist, right? And the DIIS is a slightly more complicated version of linear mixing, right? So, whereas linear mixing only considers two densities, Poulet mixing or DIIS considers a history of densities, right? And so the reason that DIIS doesn't change the answer the same way as linear mixing is that we need the norm of the density to be unchanged, right? So the norm of the density will be the same. Right. Finally, Brillouin zone sampling, right? We mentioned Brillouin zone sampling. We say in a crystal you can have an electronic, you can have a wave, an electron wave in the crystal, which has a very low frequency, a lower frequency than can be represented in the unit cell. And so this is why we need to use Bloch's theorem, right? And so we need to sample over the Brillouin zone. Okay, we need to sample over the Brillouin zone. And so effectively, I mean, all we need to do is k-point sampling. Okay, it means if you do a calculation on a crystal, you have to do, for example, a 1 k-point calculation, a 2 by 2 by 2 k-point calculation, a 3 by 3 by 3 k-point calculation, a 4 by 4 by 4 calculation, and once you find that the energy is not changing, for example, you go from 3 by 3 by 3 to 4 by 4 by 4 and you get the same energy, you know that 3 by 3 by 3 is enough. That's enough sampling of the Brillouin zone. Right now, my calculation has enough Bloch waves that it accurately represents all of the possible electron waves which can be represented in my crystal. Okay, right. That's it. That's what we're doing. Now, after the break, we're going to do some. We're going to try to do some calculations. Okay. Now, we have a problem. I can't log on to the computer in the office, right? Because I think the computer has been switched off. So at least I need to go over there, but maybe we should all go over there. All right? Yeah, because I just tried to log on to the computer and the computer doesn't respond to my login. Let me try again. No. Okay, oh, wait a minute. Maybe the problem. Oh, okay, it does work. Never mind. Oh, okay, it works. Right. So the question is, has everybody got a computer with you? Hmm? Right. So we have to decide. Are we gonna go there or are we gonna stay here?